Hello, I'm Yana Wei, and I'm excited to present our work, Grounded Image Text Matching with Mismatched Relation Reasoning. This is a joint effort with Yu Wu, Hao Zhewang, Yongfei Liu, Sibei Yang, and Xuming He. While transformer-based vision language processing models have made significant progress on various VL tasks by fine-tuning on downstream tasks, the ability of these models to understand the relationship between vision and language modalities remains to be explored. To provide a thorough study on the relation understanding abilities of the VL processing models, we present a novel joint task. This task, which we termed as Grounded Image Text Matching with Mismatched Relation, concentrates on distinguishing subtle differences in relations within the textual and visual modalities. This requires the model to have an explicit understanding of the relations across both modalities. The animation on the left offers a detailed illustration of our task. Firstly, the task requires the model to identify whether an expression describes the image. Should the image-text pair be found compatible, the model is then required to localize the object being referred to. If they are mismatched, the model should ground the inaccurately matched relation of the text. Particularly, we focus on the challenging setting of weak supervision on mismatched relations, limited training data, and out-of-distribution sentence lengths. To conduct the systematical study, we construct a benchmark for this task. We build a dataset of image-text pairs from the public referring expression grounding dataset, ref reasoning, by substituting the relation phrases to generate mismatched referring expressions for images. Our proposed dataset addresses the shortcomings of existing datasets and has the following characteristics. Firstly, compared to other relation diagnosis vision language datasets, ours includes descriptions that contain more relations and more complex language structures. The left side of the slides displays some statistics of our dataset. Secondly, human-curated test is adopted to remove the false mismatch cases in the generated data. Thirdly, we have controlled the linguistic bias of the dataset from multiple aspects. Detailed information can be found in the supplementary materials. To tackle the task, we develop a unified and generalizable framework called Relation-Sensitive Correspondence Reasoning Network, which first computes the initial representation of the linguistic and visual components, and then utilizes a context-aware correspondence reasoning network for final match predictions. The slide shows an overview of our inference process, which will be explained in the following. Given an image and an expression, we first generate visual and linguistic candidates by utilizing a detector and a language parser, and compute their respective representations. The parser also produces a language graph for the subsequent reasoning. In this slide, the ellipse denotes entity phrases, and the rectangles symbolize relation phrases. Each entity phrase is considered as one node in the graph, and each relation phrase is represented by one edge. We then leverage the context-sensitive propagation network to facilitate alignments between visual linguistic candidates. The network conducts bidirectional message propagation based on the language graph. The propagation process first initiates local entity and relation beliefs based on the similarity of their representations in both modalities, hence establishing the messages. Next, we propose a selective mechanism to aggregate context information guided by the graph and relation beliefs in two propagation directions respectively. Finally, the belief is updated using a context-sensitive gating function. Predictions for a given case are inferred by exploiting the beliefs derived from the propagation process. Especially for weakly supervised mismatched relation reasoning task, we exploit the inconsistency of the updated belief scores along the graph edges. We choose the edge with the largest match confidence difference between its two nodes as a mismatched relation. The loss computation for the matching and grounding tasks employ binary and common cross-entropy loss respectively, conducted on the beliefs. However, the task of grounding the mismatched relation is weakly supervised, hence does not have a specific loss supervision. We conducted experiments on the proposed benchmark to test several baselines of vision language pre-trained models and our proposed RCRN on inferring relation correspondences, with a special focus on the challenging setting of limited training data and out-of-distribution sentence lengths. As shown in the slide, we do experiments on two setups, where the models are trained on sentences shorter than or equal to a specific length and tested on longer sentences. As a result, our RCRN outperforms the SOTA pre-trained models on match and grounding tasks in the in-distribution scenarios, which shows the better relation understanding on limited data. Secondly, our model achieved notably better performance than the other models on all three subtasks in both out-of-distribution scenarios. The comparison also shows the effectiveness of lightweight and structured design of our proposed method. Thanks for listening. For more information, please refer to our paper and code.